Are you still here? Okay. So, okay, let's go on with the second part of quantum algorithms. We still have an hour and a half. Okay. So, are there questions about this first part? Anything clear, or something that you want me to look again, to explain? Okay. So if not, okay, I'm going on with the next algorithm, which is not so different from the previous one. This is the Bernstein-Vasirani algorithm, which is basically, okay, let's say this is the problem that solves. Okay, so we want we consider a function f, like before. It goes from 0, 1 to the n to 0, 1, and the function is such that f of x is equal to some omega times x. So returns your input x multiplied by some unknown string omega. Okay? The task is to find this string omega. Okay? Okay, yeah, okay. X and omega are string belonging to 0, 1 to the n, so these are each omega I or each xi is a bit. Okay. Okay, let me ask you again. Okay, maybe you saw something. How would you solve this problem classically? So how many times would you need to in order to how many evaluation of this function classically you need in order to find the string omega? So like before, you can evaluate f on some input x, x1, x2, and so on, and at the end, after let's say some evaluation, you get the result that is omega. So how many evaluation? Yeah, okay. I see that you are getting on the chart. It's n evaluation. Okay, classical solution, you need n evaluation of the function to recover w, omega, I mean. Why? Because you can consider this this input. Okay, the input are there is only one in each position. So you have 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on up to the end. So 0, 0, 0, and the last is 1. Because when you multiply this input with omega, this returns the, for example, the first line returns the first element, because if omega 1 is 1, then the output is 1. Otherwise, if omega 1 is 0, the output will be 0. So with this first evaluation, you retrieve the the first element, the value of the first element of the first bit of the bit string omega. Okay, so it's n times. Okay, and this is classically okay. The classical solution is this one. So quantum solution, Bernstein-Vasirani came up with this circuit. This is exactly the same circuit that we have seen before for the Deutsch-Jozsa algorithm, but with a different, of course, U of f. And so using the same circuit, you can also solve the problem of finding this string omega faster than you will do classically. Okay, so the algorithm is basically the same. So we're gonna see the step-by-step solution, but which is basically the same that we've seen before, but with some differences, because the function now is no more function balance or cosine, it doesn't matter. The function now is omega times x. Okay, so let's see how the algorithm works. As we've seen before, we start from the 0n1 state, which means 0 bits, n bits in the 0 state, and the last one in 1. So this is the first register, this is the second register. The first register has n bits. Yes, it's an inner product, so it means, yeah, you multiply. It's the product when you have strings. So you basically multiply. I mean, no, sorry, it's not a. So okay, here you get. Yes. I mean, you get a single number in output. So you get. So basically, the product is this one. So you get. You do omega 1 times x1 plus omega 2 times x2 plus, and so on, omega n times xn. So it's like this. So and the output. Yes, sure. Yes, we need. So also the function goes from this to 0, 1. So it's the scalar product between strings. Okay, between bit strings. Okay. Okay. Okay, we are here. No. In the output you have a number, so you get 0, 1. So you multiply element wise, but then you sum everything. No, it's like the scalar product, okay, between vectors. Okay, but the sum is the sum modulus 2. Okay, so we have. Okay, we apply the gates Hn and H to the initial state. What you obtain is the following. We have seen it before. So Hn applied to 0n gives you this state, which is the linear superposition of all possible bit strings, and 1 to which is applied to H gives you the minus state, so 0 minus 1 over square root of 2. Let's go on. Okay, we apply the U of f this time, like we have seen before in the Deutsch-Jozsa algorithm. Okay, x, the effect of the U of f is the one shown here. So, which means that when you apply it, we get until here everything is the same, but then things change inside the parentheses, because here you get 0 plus omega times x, which again is omega times x, minus 1 plus omega times x over square root of 2. You can write again, like we did in the other algorithm, in this way. Why? Because when omega times x is 0, this state here becomes 0 minus 1. When omega x is 1, you get 1 here minus 1 plus 1, which is 0. So you get a minus in front. And you can write everything in this way. So you you add this minus 1, you multiply everything by minus 1 times minus 1 to the power of omega times x, okay, in order to, which is essentially equal to this other state, okay. Again, so we reach this part of the algorithm where we discard the last register, which we were not interested in anything concerning the last register, and we apply hn to what remains. Okay, h of n again is this part here. The operator h of n can be written in this form, and we have already seen this before. This is the state that we have at this point. And so we apply hn to this state. Again, like before, what happens is that there is a scalar product between z and x, which means which generate a Kronecker delta, which means that this scalar product z x becomes 1, and every time you see a z, it becomes an x. So you will have here an x, which is multiplied with this term. So at the end you get something like this, okay? Z and x go away because this is scalar product between z and x, and you're left with this term, which is this one here, where x became where z became the x, plus this term here, which is this one. Again, you can see this as a quantum state where the basis is y, and it's a summation. It's a superposition of a state like this, where superposition of y state with amplitudes, with complex coefficients, that define the probability amplitude, defined by the term that is inside the parentheses here. Okay, so we're left with this state. If you look here, you get the following. If you assume to measure y equal to omega, let's see which is the probability. The probability is, so you substitute y with omega, and you get omega times x plus omega times x, which is this one here. We group together the two omega. So it's omega times omega multiplied by x. You know that when you multiply omega times omega, you always get 0. Okay? So it's minus 1 to 0, which is 1. Everything square gives you a 1. So the probability of finding in output, so of measuring the string omega in output, is exactly 1. So again, like what happened for the Doijos algorithm, with just one evaluation, so with just one run of the algorithm, so one evaluation of the function in quantum terms, you recover omega in the output. Okay, so you just run it one time, and the n output will be exactly the bit that compose omega, which is the string that you want to, the string that you're trying to find. So this is again you get you beat the classical case where you need instead n evaluation of the function to recover omega. Okay, is it clear so far, this other application of basically the same algorithm? Are there questions? Write in the chat if you have something or if it's okay. Or are you lost or something? Okay, it's basically, yeah, the same that we've seen before. There is just this trick at the end, no, with the probability. Okay.
I have a quick question just to understand, to see if I understood. So at the previous step, you discard the last register. Is that because that corresponds to the one passed through the Hadamard? Is that term exactly that input on the bottom, and
yes,
so you discarded?
Yes, exactly. So it's this one, yeah. So it's this line here. So it's the original one that then went through the Hadamard, and then the U of f together with this register here. But then, I mean, the result is, so what you get here is something that is, as you can see, this is the state. If you measure it, you get something that it's half of the time 0, half of the times 1, but doesn't carry any information about what you're trying to solve. So you just don't consider it. Yeah. So
Okay.
well, yeah, it's the original one. Yeah.
Okay. I mean, is because at the beginning of the lessons this morning you were defining the Hadamard of 1 equal to this term, and that's the one that goes away.
Yes, this is the one here, the Hadamard. But then this state was also subjected to U of f, and by chance happen to have again the same state after the U of f, but in general may not be true.
Okay.
So, but okay, since yeah, so we don't do anything with this. We're just interested in what happens to the first n qubit, the first n register. Basically, in other terms, okay, the last register is used to store at some point the value of the function calculated in x. But then, as you can see, you can rewrite everything. I mean, the information here that you get in the last register is already in the first register in this way. Okay, so it's the power. Yeah, it's something that is I think is called phase kickback. Okay, so you get some information here in the last register, so in the last line, but then at the end it's like having it also on the first register. Okay, so you can discard the last one. So it's one trick that is used in this kind of quantum in quantum circuits. Okay, probably now it's more clear. Okay, let me go on with another algorithm that is the Simon algorithm. So what is the Simon problem? Basically here, you're given a function, again, but this time the function goes from 0, 1, n to 0, 1, n. So also the output is a string. And this function is such that there exists a p, some string p, some bit string p, that for which f of x plus p is equal to f of x for every input that you have. So the task is to find this string p. Okay, here we have an example that explains you better this problem. So here we have all the possible x's and f of x of this kind. So you have a few seconds to try to guess which is p. So basically, if you can see, there is, I don't know, okay, this term, if the input is 0, 1, 0, f of x is 0, 0, 0. But also if the input is 1, 0, 0, the f of x is 0, 0, 0. So you want to find the p such that x plus p equal to f of x. So can you guess what is p? Can you write it in the chat for this example? Remember, okay, look at, yeah, of course, look at inputs that have the same output and try to guess which is the p. Is it clear, the problem? Do you want me to go previous slide, or? So let's say how many of you are trying? Write this in the chat at least. Okay. So okay. So you have a function. For some, let's say, you have some function, and you have also, let's say, an input x. For this input x, there exists a p for which x plus p gives you the same result. Okay, and this is also true for every x. So for every x, this p, there is this p that works on every x. Okay, I see some people are giving an answer. So the answer is 110. Yeah, okay, some of you got it right. So for example, take okay, now take this 0, 0, 0. Okay, you have to focus on state that give the same output. So where f of x is the same. So let's say this one that has output 0, 0, 0, and this one that has output 0, 0, 0. They are 0, 1, 0, and 1, 0, 0. So let me write on the other. Okay, let me. Okay, so we have f of what? 0, 1, 0 is equal to 0, 0, 0, and f of 1, 0, 0 is equal to 0, 0, 0. So we're looking for the P such that
Ricardo,
yes,
do you want to show
yeah,
the tablet?
sure, right. Okay. Okay. You have something like this. So we know these two, and we want to find P such that, let's say, f of 0, 1, 0 plus P is equal to f of 0, 1, 0. Okay? And we know that 0, 1, 0 plus P is equal to 1, 0, 0 because we have found it, right? Are you okay with this? I think it's clear. So what is the number that if you sum it to 0, 1, 1, you get 0, 0, 1, 1, 0, 0, I mean, it's exactly 1, 1, 0, because you get, so it's 0, 1, 0 plus 1, 1, 0, which is this with this one, you get 1. This with this one, you get 0. This with this one, you get 0. So you get it. And it is P. So P is 1, 1, 0. Another way of finding P is you should do P equal to 1, 0, 0 plus 0, 1, 0. So it's the same. You just put this on the other side. And this is how it works with the binary, okay? So you sum these two and you get P. Same happened. Same would have happened if I choose 0, 0, 0, which has f of x 1, 0, 1, with one with the same f of x, which is what? Which is this one. So 0. In fact, if you see 0, 0, 0 plus P gives you this one. Okay. So this is the way you do that classically, basically, no? So in general, okay, let me be more formal. Okay, if you want to find P, what you have to do? You have to consider M strings. Okay, consider M different strings, input strings, and check if there are 2 of them for which f of x is the same. If so, like we did, okay, this should be true, which means that P is equal to xi plus xj. But you have to be clear enough to choose 2 inputs for which the outputs are the same. For example, if this was a very large list and you don't have access to f of x immediately, like in this case, you can start with this, with 0, 0, 0, and then try 0, 0, 1 and see the result. But then they are not the same value of f. So you can try 0, 1, 0, and so on, until you find 2 which have the same, until you find 2 inputs for which they have the same. The plus is the modulus 2. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1, 1 plus 0 is 1, 1 plus 1 is 0 again. Okay. So, okay, this is clear. No? So if I consider M strings, no, the total number of checks that I have to do is all the pairwise checks. No, you have check x1 with x2, then x1 with x3, and so on. x2 with x3, x2 with x4. And what you have is you do with m strings. You have to do m times m minus 1 over 2 checks. Okay. Then what is the probability of selecting a random m strings and finding p? Probability is given by the number of checks that I have to make over the total number of strings. If I want this probability to be greater than 1/2, which means this one greater than 1/2, my m, the number of input strings that I have to consider must be strictly greater than half of the total space. Okay. So is it clear, this part? So this is the classical solution. No? Of course, if yeah, like before, you can be lucky and find it immediately. So immediately you get 0, 0, 0, and you get an input, this one, and where is it? And this one, yeah, and you're very lucky, and you just do it one time. In the worst case scenario, you have to consider m strings, where m is greater than half of the total number of strings that you can have. Okay, so as you see, m scales grows exponentially. Okay, with the number of bits. Okay, are you okay with this? Please write in the chat if there are questions. Because now we're going to see the algorithm. Okay, the algorithm looks basically the same, but has some differences. Okay, in this case, we also have hn, so n register here, and then an n register here, and we also measure at the end both. Okay, u of f act always in the same way, but f this time is different. So let's start with the step-by-step analysis. Okay, the initial state is this one, and is pretty clear. We apply h of n only to the first register. The second one is unchanged. Then we apply u of f. U of f again performs the thing that we have seen before, but in superposition. Okay, so we simply apply the definition, but since we have a superposition, the f of x is inside. Okay, this summation. Okay. So at this point, after the evaluation of the f, we are left with this state here. Now, what we do is measure the second register. So suppose we measure f of x tilde. So we measure some, so we obtain the result associated to some unknown f of x tilde. I mean, associated to some input x tilde. So the state, which initially was this one, after the measurement, collapses to this state here. So measuring the state here, you get something like this, but then the measurement reflects, affects also the state of the first n register here. So in this summation, the only terms that survive are those associated with the input that give me f of x tilde as output. Which are these two terms? Are x and x plus p. At this point, we do not consider anymore f of x tilde, and we focus on the first qubit, the first register of qubits here, and we measure them again. We first apply the Hadamard gate on all of them. So this we know is the Hadamard, and we apply it to this state here. What we get, again, the same, okay, here we get a scalar product between z and x, and the scalar product between z and x tilde plus p, which means that in one case it becomes a sum. In one case, z becomes equal to x tilde. In the other case, xz become equal to this one, x tilde plus p. So we have at the end this term here. So is -1 y times x tilde plus -1 to the y times x tilde plus p y. Okay. Again, so this inside the parentheses is with the 1 over square root is the probability of obtaining as output a given string y here. So in the first register of n qubits, yeah. So this is the probability of obtaining y. Are you with me so far with this probability? Because then, as you see, the trick is often in the now you look at the probability. Okay. So maybe okay, seems great. Okay, or ask questions with your microphone. Okay, also if you want more questions, you need some clarification. Okay, then. So let's go on with the probability. So this is our probability. Notice that if if p times y, so this multiplication here, y times p or p times y, is 1, what we get? We get that this term here becomes equal to here y times x. Okay, because if p times y is 1, okay, we are left with this one, which is, I mean, inside the parentheses we have two terms that are one of the opposite of the other, which cancel each other, and what we get is 0 probability. So what does it mean? It means that the probability of finding y such that p times y is equal to 1 is 0. So, since this is scalar product and the only possibility are 0 or 1, we always measure in the output y such that p times y is equal to 0. Okay? So, in order to recover p, we need to have at least, since p is a string of n bits, we need to solve this linear system. Okay, we need at least n of this linearly independent equation to solve, to find p. Now the question becomes, what is the probability of having in output y1, y2, yn, ym the probability of having strings which are linearly independent, which means that you can construct this system of equation. Okay, the probability of having them linearly independent is this one. So it's 1 minus 2 to the m over 2 to the n. And you can show that since, so in order to be sure to find a linear independent set, we have to repeat the algorithm a number of times equal to 1 over the probability of finding in output strings that are linearly independent. So 1 over this probability here is a number that is between 1 and 2. What does it mean? And you have to do it times n. So this means that the complexity of the Simon algorithm, so you have to evaluate, so you have to run the Simon algorithm a number of times equal to 2, at most to 2 to the n times, in order to find this set of linearly independent equation that allow you to retrieve P, okay? Which is exponentially faster than classically, where we have said before it was 2 to the n over 2. Okay? Okay, we've seen it before that it was, yeah, it was growing to, like 2 to the n over 2. Yeah. So this was a little bit more complicated. I hope you follow. Are there questions on this algorithm? Previous slide. Okay, the probability. Which probability? This one.
Yes, basically
Okay.
You mentioned an implication that p dot y has to be 0.
Yes.
I got lost there at this point.
Okay.
At the end of your demonstration.
What happens here? When p times y equal 1, okay. Okay, let me write it here on the. Okay. Let me go here. Okay, we had, sorry, I don't remember. So we had minus 1 y times. Okay, we had something like this. When y times p equal 1, what happens? So this can be written as minus 1 y times x plus y times p. Okay, so it means is equal to minus 1 y times x plus 1, which is also equal to minus 1 y times x times minus 1 to the 1, right? So that's why I get, yes, I get here a minus, and okay. Is it okay? Okay, there is also another question that was exactly this. Okay, that's why you get 0, because these two terms are the same. So this is the reason, no? Okay, okay, I think it's good. So again, if you want, so whatever answer you get, whatever way you get, it's gonna be a scalar product with p is gonna be 0. In order to retrieve p, you need n of them. You need to solve this linear system. the probability of finding this linear system at the end is this one. So how many times you want to run the circuit in order to find this linear independent set? 2 times. 2 times n times. Okay, which is exponentially lower than the classical solution where you have an exponential time, an exponential number of times where you have to evaluate the function. Okay, is it clear? I think now. Is it clear?
But it's 2n times at most, at the worst, isn't it?
Yes, of course.
Could be less.
Yeah, at most, yeah. It's in fact the probability is a number that goes from 1 to 2. Yeah. I mean, not the probability, the number of time. 1 over the probability is this number here. Okay, it's something complete between 1 and 2. So, okay, we can go on and see the quantum Fourier transform. Quantum Fourier transform is another algorithm that is very famous. Is used in other quantum algorithms that are we're going to see them, and which are much more important. So, first of all, what is the discrete Fourier transform? So you have a function from some input G to from input space G to the complex space C. The discrete Fourier transform is defined in this way. Okay, it's a transformation. It's a summation where the coefficients are e to the 2 pi I kj over n. So the phase is like this. Okay, this is the discrete Fourier transform. Okay. Basically everybody knows what this is. There exists a quantum version of it, which is the quantum Fourier transform. So given a basis state, which means a state like 1, 0, 0, 0, 1, 0, okay, state of a qubit basis state of the basis, okay, not a superposition. Okay, so the quantum Fourier transform transform your state Gj, could be 1, for example, into a superposition of all the basis states multiplied by a coefficient that is again the same that you have in the discrete Fourier transform. The simplest quantum Fourier transform possible is exactly the Hadamard gate that does exactly this. So the Hadamard gate, you know, it is the transform the state 0 into 1 over 2, 1 over square root of 2, 0 plus 1. So it's the simplest case of quantum Fourier transform. Okay, and you can see, no, that this is a general form, no, of quantum Fourier transform. So when you apply, what happens when you apply, when you're given a state psi, and you apply the quantum Fourier transform to this state? Okay, the quantum Fourier transform so this basis state here into what we have seen before. So at the end, you get something that looks like this with the same coefficients. Okay, so it's a summation both on the J and on the K. Okay, suppose now that I have a number J that goes from, that could be one, could be a number in, I mean, belongs to the set 0 to the n minus 1. So it could be any number in this set. Could be, if n is 10, could be 2 to the 10 minus 1 at most. Okay, so the number of elements in this set is 2 to the n. So j is just a number, okay? A number means that in binary, I mean, you can also transform a number in binary, okay? So it's going to be, again, an input string. I mean, j is going to be a bit string, okay, of some dimension n. Okay, but in general, j could be a number between 0 and 2 to the n minus 1. Okay? The quantum Fourier transform acts like this. So transform the state j, as we've seen before, in the state shown here. So it's a summation over k from 0 to 2 to the n minus 1 multiplied by this phase k. Again, okay, you can think of the Hadamard gate applied to n qubit as a special case of quantum Fourier transform, okay, where we have seen before that what happens. Okay, let me go to the. Okay, you have seen before that when you apply no, it's not here. Okay, when you apply h n to 0 n, what you get is something that is like sum of x 1 over square root 2 to the n. Okay, it's a special case of quantum Fourier transform. Okay, j. So here j. In this case here j is the 0, 0, 0, 0, 0, 0, which is 0, let's say. But in general, you can have j equal to whatever number, so 54, which is some binary string. I don't know which binary string is 1, 0, 1, 0, 0, così. Okay. So this is the meaning of the quantum Fourier transform. Okay, it's a special case of I mean the Hadamard on n qubits is a special case of quantum Fourier transform. Okay, so since we have to construct a state with a number of amplitudes that is exponential, so it's a summation of an exponential number of terms, is it possible to realize such transformation efficiently? So only using a polynomial number of resources of gates using a quantum computer? The answer is yes. So basically, you can prove, it's possible to prove that the quantum Fourier transform can be also represented in this way. So we can rearrange all the terms and apply some mathematics to transform this state into this other state, which is a tensor product of many qubit states. Okay, so it's a tensor product of n qubit states, of course. Okay, but each one is 0 plus some phase 1. Okay, in this case of Hadamard, in this case here, what is our way of writing it? It's basically sum L equal 1 to n of 0 plus 1 over square root of 2. Okay, so it's basically the same thing. Okay, but in a more general case. Okay, is this one. Okay, and there is a circuit that realizes exactly this transformation, which is this one. Okay, you can see that you have n qubits. To each one is applied a Hadamard and then some control rotations. Okay, you understand that this case here is a simple case where you only have the Hadamard, of course, and no rotation, no control rotations. Okay. So in general, okay, you can write. So the circuit that realizes this function here is this one. Are you with me so far? Okay, visible. What is the exponent? Okay, of the 2. 2 to the L here. 2 to the L. L is the summation. I mean, what is the purpose? The purpose. Yeah, in some sense, yes, it's okay. I mean, there is no purpose, I think, on the QFT alone. Why you need it? You need it because, I mean, we will see later. I mean, it constructs a superposition where the phase, yeah, depends also on J. More or less is this the meaning. Okay. But yeah, taken alone, I mean, no, depends then on the application. I mean, there are other circuits that use the quantum Fourier transform as a subroutine, and they use it to achieve a speed up with respect to the quantum to the classical case. Basically, it's useful because it creates a superposition, like we have seen for the H gate. Maybe it's easier to grasp, no? The purpose of the HN gate is to create a superposition in such a way that you can compute in superposition multiple things. And this is something similar, but with the addition that you also have a phase. Okay. Yeah, somehow, yeah, this is also true. Huh? It's like, but yeah, the main purpose is that, like for the Hadamard N gate, is that you have quantum superposition. Okay. With a particular phase also. Okay. I don't know, I'm skipping this, I think, because so this is the proof that you can transform this state here into this product here, tensor product here. And you can see it by yourself. Okay, you just employ this fact here, which is the basically is the way of how you write a number in binary form in this way. Okay, and you employ here in the exponent, and at the end you get this one. So as I said before, is it efficient to construct this state with 2 to the n amplitudes? The answer is yes. And let's count the number of the complexity of the algorithm, which means the number of gates that you need to use in order to construct this exponential the superposition of an exponential number of terms. Okay, so here we have n qubits, and to each one is applied an Hadamard gate. So we have n Hadamard gate. At the end, here we have n/2 swaps, because we swap the first with the last, the second with the n-1. Okay, and then we apply a number of control gates, where control gate is Rk is defined in this way. So it's 1, 0, 0e to the I to pi over 2k. And we apply it how many times? In the first case, you apply n-1 times. Then for the second qubit, you apply n-2 times, and so on. The total number of times that you apply them is n times n-1 over 2. So at the end, you get n plus n squared, n plus n over 2 plus n squared over 2. So the dominant term is n squared. So at the end, you get something that grows like n squared. So a polynomial with n squared being the largest term. Okay, so you can the thing that I want you to understand is that you can compute, okay, this kind of state with just a polynomial number of gates. Okay. Till now, I don't see, but I guess. Okay. Let me check the chat. I'm not getting what you mean, Cedric, but okay. Please characterize your face. Over half of the available qubit could be bound to forever. Okay, let me go on because okay. So let's see the first algorithm that employs quantum Fourier transform in order to perform some specific task. Okay. If are there other questions, or Cedric, if you can formulate again the question, because I don't get it.
Yeah, it was just reasoning by analogy with classical physics and Fourier transform. If you comb your phase space with with sampling only half as much as you would in a different experiment, you would get with a Fourier transform some spectral representation of a signal, in that case of the qubits. It would be less precise, but you would get an idea of what the result that you observe, what you're observing is like. You would get some idea of it, less precise, but you would. In this case, by analogy, if you were to act on only the half of the available, for instance, half of the available qubits, and I'm not sure this makes sense. Okay, could you by analogy with classical Fourier transform, could you actually bound your error in some way? Is it possible to? The question is it possible to actually measure your error, or at least bound it? Does it make any sense? Maybe not.
Because,
I'm sorry.
I mean, here, what's the definition of error in this case? In the quantum case, not sure about this.
Well, yes, you're right. I don't know what the result will be at the end. Because
at the end here, what you get is so something similar to the Fourier transform, but it's only in the superposition. I mean, everything is in superposition. So you don't have access to the to the superposition unless you measure it. But then measuring means distracting the quantum state of the Fourier transform. So probably there is some difference that because I'm not aware about the error part in classical Fourier transform. But here I think maybe probably is fundamentally different because it's only it's only a large superposition. Yeah, like in the case here. I mean, if you do it not if you do the Hadamard not on all qubits but just on some of them, then you just have a smaller superposition, and with other qubits being still in the zero state. So you don't span the full 2 to the n. You don't span the full space. Okay? You just restrict to a portion. So I don't know if this makes sense.
Yeah. So that was exactly it. And so the result, how would the result compare to if you span the whole qubit space? Exactly. No.
Okay.
Yorgos just nailed it. Basically, that's it.
Okay.
Yes.
Okay. Perfect. Okay. Okay. Let's go on with the quantum phase estimation. I think we have still 20 minutes. Okay, gonna be probably the last algorithm. We're gonna see it in the afternoon because we don't have time now. But okay, it's fine. Quantum phase estimation. So this is the problem. The problem is given a unitary operator, so U, and the quantum state, which is an eigenvector, eigenstate of U, such that U psi equal to some phase, some e to the 2 pi I theta psi. The task is to estimate psi. This is, again, here, I mean, this is a problem that is very much related to quantum computation, okay? Doesn't look like something that you could use in some real application, okay? Because here the objective is, here you have your unitary operator and your quantum state, then try to estimate the theta that appears in your eigenvalue, okay? This is the task of this problem. Then later we will see how to use it in a real world case, okay? So the quantum Fourier transform circuit looks like this. So we have a 0, 0, 0 state, so n of them, psi, that is the quantum state of which we want to calculate the phase, so the theta that appears in the eigenvalue. Okay, this is our register. We apply Hadamard gates and control U gates to the psi. So U is the unity that you are given. U to some power means you multiply U many times, no, until you get this one. So U 2 to the 0 means U to the 1, which means basically only U, only the U operator. Okay, you apply this control operation, and then the quantum Fourier transform -1 to the -1. So it's the inverse quantum Fourier transform, which is basically obtained by reversing the circuit. Then what you do is measuring everything, okay? Okay, let's go with the step. Let's say I'm not going to be like a step by step, but because it's much more complex than the previous circuits, but we're gonna see block after block what changes in the state. Okay, at the beginning we have this kind of state here that okay, we now we know well what it means. After application of the Hadamard gate on the first n qubits, you get this state here, of course. Okay, so it's again the Hadamard on all the qubit, on the 0 qubits. Okay, you get something like this, which is again what I wrote also here is the same, writing in this way, times psi. After the application of this control U gate, you are left with this state here. Here it's a bit strange, but you can write everything. You can apply the control operation and write everything in such a way that psi is left unchanged at the end, and everything is in this. Everything is in the superposition of the first n bits that were originally in 0. It's like it's very similar at the end to what we have seen before, no, with the other algorithm. No, at the end you get some state that is left unchanged, and with something that is a phase kickback, you get a property, no, of the last register into the first register. Okay, so here the property being this one, so the theta. The fact that U applied to psi gives you this term. That is what appears here also. Then with the quantum Fourier transform, this term here becomes so you apply basically, as we have seen before, the quantum Fourier transform to K, and you return to the J. Okay, and you get another phase which is 2 to the n J that goes inside this the exponent. Okay, so at the end, the thing that I want you to understand is that at the end you get a state like this. Okay, and you can do the math and by yourself and try to see that this is what happens actually, you know, at the end of the circuit. Okay, now it's a bit complicated, much more than the others, than the other circuits. So I'm gonna skip it and just show you the result.
So QFT inverse is just reversing all the steps, starting from the end and going toward input in the previous circuit.
Yes. Okay. Then what you do? Okay, you have this state, the initial state, which is this one. Okay, I mean the state at the end. You can see this again as a state, a superposition state where the basic state are these two, where the superposition is on J, and this inside here is the probability amplitude. So this means that the probability of measuring J. So as you see, again, the last qubit, the last state psi is discarded. It's not measured. Okay. However, the probability of measuring some output J will be this term here squared. Okay, so yeah, this term here square. Okay. What happens now? It happens that you see that if J is equal to, so J is the output string, is equal to 2 to the n sigma, then the probability becomes 1. Because if you see here, if you substitute 2 to the n theta, this becomes 0, which means that the whole probability becomes 1. So what does it mean? It means that with probability 1, so every time I run this quantum phase estimation algorithm, I get at the end, because the probability is 1, a bit string, which is the binary representation of theta. So the state of the measurement, of course, is going to be psi, which is left unchanged, 2 to the n theta. So let me briefly recap everything. Okay. The idea here is to, what I want to do is to estimate theta. Okay. So to understand what is theta, I have u and I have psi, such that u psi equal to e to the 2 pi I theta psi. Okay. I employ this circuit, which has n qubits here, and here we have psi with this control unitary, where u is the matrix that the operator that we're given. We repeatedly apply this control u, and then the quantum Fourier transform, the inverse quantum Fourier transform. Then we measure and add the output we get by looking at the probability. We see that the probability of getting an output that is exactly the binary form of theta is 1. Okay, so after the quantum Fourier transform circuit, I obtain as a measurement I know the state I know the phase theta that I was originally looking for. Okay, is it clear more or less? Write it. Okay, write it in the chat, or ask me a question with your microphone if you have one. But okay, this is the idea. However, keep in mind, because of course, I mean, the mathematical formulation is quite complex. You have to skip some part, but the idea is the following. So you have this circuit that allow you to have theta in output. So the theta that you're looking for is the one associated with the state that you are using, and the unitary matrix whose eigenstate is psi. Okay. Just one yes in the chat. What about the others? Is it okay, more or less? So don't be shy, write in also no is okay. Then we will take the.
What I'm saying, Ricardo, is sorry, is from the very beginning, from the very first circuit that you described. Don't go back.
Okay.
You use the implication: if for instance, for this last one, if j equals 2 to the nth times theta, then the probability becomes so. And so when you measure the result, when you observe the results j, what I'm not clear on is logically you will observe some sort of result.
Yeah.
And
No, I mean,
then you will deduce the property theta is from that result. Is that it?
Well, I mean, probably here is not very clear the logical order, but okay. I mean, what I mean is that this is the probability. Okay, it's the inverse. Okay, so when this probability is 1, probably it happens only when j is equal to 2 to the n theta. I mean, for all
That's
the
clear.
other,
That's clear.
I mean, for all the other j's, what does it mean that the probability of this string is 1? It means that the probability of all the other strings is 0, because the probability must sum up to 1. Okay.
Well, that's where I have an itch, because I understand theta is multidimensional. It's not just one scalar. And so there might be several ways of achieving that probability of 1. Several ways meaning several values of j and theta. Obviously, they're related.
Okay, theta is just one value, so it's
okay.
So theta is unique. Is defined by this equation. Okay, is the eigenvalue of psi associated with psi, where u is the matrix. Okay.
Okay, I thought it was multidimensional. Sorry. Okay.
Yeah, at the end, I mean, at the end it's a number, but here you represent it in binary. J is a number, but it's also what you get here is you get 1 and zeros, okay, in the measurement. 1 and zeros are the bit string that in binary tells you which number is j, because j is a number from 0 to 2 to the n minus 1. Okay, well, maybe okay, now it's more clear. Okay, however, let me go on with the Shor algorithm. Okay, I'm not gonna go in detail with the Shor algorithm because it's quite complicated, but the idea is the following. Okay, the Shor algorithm solves the factorization problem. What is the factorization problem? You get n, a large number, and the task is to find the prime numbers such that n equals p times q, such that multiplied give you n. So for example, if I tell you n equals 15, p and q are 3 and 5. Okay, usually n is very large, so it's a number of thousands of digits, which means that in order to find p and q, finding p and q is hard. Actually, it takes exponential time on a classical, or even in a classical supercomputer. Okay, and that's why this problem is at the core of the currently used crypto systems. Okay, the RSA crypto system. Okay, where this and this is the core problem at the problem at the core of security nowadays. Okay. The Shor algorithm, what does it do is to employ a modified version of quantum phase estimation to solve the factorization problem. And this algorithm, this is Peter Shor, that in 1994, something like that, proposed this algorithm to solve factorization in polynomial time. So that bits exponentially achieve an exponential speed up with respect to the classical case. Okay. So that's why, so quantum phase estimation alone seems not very useful, but then you see that the application is huge. And the genius of Peter Shor was to actually formulate the factorization problem as a problem of finding, of estimating the phase of a unitary operator. Okay. So briefly, the idea is the following. Peter Shor was able to formulate the problem of factorization, reformulate it into a problem of finding the period of a function, and finding the period of a function to the problem of quantum phase estimation. That was the trick that he employed. Okay. Finally, what happened? This is just a simple graph showing the runtime. No? On red, you have the best classical algorithm, which is the number field sieve, which solve the factorization problem and solve it in exponential time. So even if we had this algorithm solved by the most powerful supercomputer, so an HPC supercomputer nowadays, it will take billions of years, so something of the order of the age of the universe, in order to factorize a number with 2000 digits. Okay? Because this is the number of operations needed by this algorithm. For what concerns the Shor algorithm, instead, there is this exponential speed up, exponential advantage with respect to the best classical algorithm. And since it only needs polynomial, a polynomial in the sides of the problem, and assuming because the number of gates that it employs is efficient, so it's a polynomial. Okay. And assuming that we have a quantum computer which is ideal computer with which is fault tolerant, which means that do not have errors, which is capable of which is large scale, so capable of executing Shor algorithm on this problem of factorizing a 2000 qubit digit number, then this computer will take just seconds to factorize such number, assuming again that the speed of application of single gates in this quantum computer is basically the same that we have today on superconducting computers. So given these assumptions of fault tolerance, of large scale, and a speed that is in accordance with what we have today, Shor algorithm executed by this computer will only take seconds. Okay, so this is the power of this kind of algorithm, and an algorithm that in the 90s gave to the topic a lot of a boost. So a lot of attention was given to this topic of developing quantum algorithms. Okay. Yeah, this is just the idea of a short algorithm. The last one is going to be Grover search, but we since it's 12:30, we're gonna see it after lunch.
Yes, I agree.
If one thing, if you have questions concerning this part, please write in the chat or we can postpone the question session later after lunch.
Everybody, I think, is angry. So it's time for lunch. And let's wait a few minutes. But okay. Good.
Okay, there is some mathematics, but yeah, I guess it's the only way once in a lifetime to have more or less clear idea of what's the quantum computing topic is about. Yeah, maybe it's a bit painful, but
It's necessary.
yeah.
Okay. Congratulations, Ricardo. See you in the afternoon at 2 p.m. Thanks a lot.
Yeah, see you later.
See you later. Math is good, I agree with you. Bye-bye.
Bye.